Alright, hi Year 12s, this is Mr. Lim here again, and this is our video on Ka, Kb, and amphiprotic substances. So let's get started. This is what we're going to learn. Okay, so let's have a look. So, as we've seen in equilibrium, K values, right? So we're now looking into Ka and Kb. What are they? They are the K values for equilibrium systems established when acids and bases are placed in solution. Ka for acids, Kb for bases, duh. Right, so strong acids and bases, remember, they completely ionize. Thus, they have very high K values, and they only have products and no reactants. Okay, so for example, if I have HCl plus H2O as a single arrow forming H3O plus what? Plus Cl minus. Then what's going to happen is that, even if this is a gas or an aqueous, this is liquid, this is AQ, this is AQ. So the K expression for this is H3O plus and Cl minus over HCl. No water because that's a liquid, right? So because all of them are like this and there's none of this, so if this is all of them and none of them, you're going to just have an extremely high value or very close to infinite. So the idea is that these strong acids have a high K value, right? However, weaker acids and bases, right, only partially ionize, and thus their K values is an indication of the ratio of products to reactants of a hydrolysis equation of the acid to base. So let's do a weak acid. So we have CH3COH, AQ, plus H2O liquid to form, and go back to H3O plus AQ, and ethanowate ions. So therefore the K value will be here, H3O plus, these are square brackets, okay, with ethanoate ions over the ethanoic acid, right? Okay, and so hopefully we remember that because this is a weak acid, lots of them are here and very few of these. So you're going to have a few over lots, and therefore the K value is going to be very, very low, right? So that's for a weak acid. However, right, if you have these two acids, like this value here for the, let's say that the ethanoic acid value is 1.8 times 10 to the negative 5, okay, which is a very small value. If you had another acid, just like, say, HX, right, and its K value was 1.9 times 10 to the negative 6, okay? So we would compare these two values, this K value for HX and this K value for ethanoic acid, and we would be able to say that the higher of the K values is a stronger acid than the lower K value, right? This all affects their pH and their conductivity, so which one is the higher value, right? Just because it's 1.9 doesn't mean it's the higher value. You've got to take into account this. So this is 10 to the negative 6. This is much smaller than that. Okay, because this is smaller, there'll be less hydronium ions. Because this is bigger, there'll be more hydronium ions if you're dealing with the same temperature and same concentration. And so therefore, this will have more conductivity because it have more mobile charge particles, and it will also have a lower pH because it'll be more acidic. All right, so the idea is that you compare K values to work out of the weak acids which one is stronger, and the higher the value, the better. Okay, so let's move on. The K values for acids and bases also give an indication about the relative strength of their conjugate pairs. Okay, so in that last example, I just had ethanoic acid with a Ka of 1.8 times 10 to the negative 5, and I had a hypothetical acid which with a Ka of 1.9 times 10 to the negative 6, okay? So we know that this one is a stronger acid, okay? However, the conjugate of strong acids are actually very weak, right? The idea of strong acids, they completely ionize, their conjugates don't actually try and pull off any of the hydrogens in the water. So they are very weak, close to the point of neutral. And conjugates of weaker acids are stronger bases. So if we were to look at the conjugate base of ethanoic acid, which happens to be CH3COO minus, and the conjugate base of this HX, this theoretical thing, right? This X minus would be the stronger base, okay? Because it is a weaker acid. It is a weaker acid. Therefore, its conjugate is a stronger base. It is more likely to pull off a hydrogen off a water and form into HX because this has a much lower Ka value. All right? And if you were to really talk about these things, the Kb value, where can I write this? Kb value, whoops, that's a little b. Okay, the Kb value versus this Kb value, this one would be larger than that one, right? Because it's a stronger base. Okay, so the conjugate pairs of those things, the weaker the acid, the stronger the base, and vice versa. Okay, let's move on. So let's go on to this next idea. Amphiprotic, this word. Amphiprotic substances are substances that can accept or donate protons. So they can do both, right? They can do both. An example of this is the hydrogen phosphate ion. So the hydrogen phosphate ion, HPO4 2 minus, with a bit of water, can do this, right? Or it can do this, all right? Where it does this. Okay, so here the proton is being donated that way. No, wait, no, it's not. This proton here is being donated to there. And in this case here, this proton is being donated to there. So in this case, in the top case, it's acting like a base. Oops, that's not what I want. It's acting like a base. And in the bottom case, it's acting like an acid. All right, so it can accept or donate protons. All right, because this one at the top is acting like a base, this will have a Kb value, and this will have a Ka value. All right, so it can accept and donate protons. Other things that can do so are the dihydrogen phosphate ion or the hydrogen sulfate ion, right? But this one is just an example, right? So amphiprotic substances, as I said, will have a Ka and a Kb value before their two possible reactions. Whichever value, the Ka or the Kb, is larger, will occur more often, and thus the overall nature of the substance is determined by these two values or their relative values, right? So if I was to say that, now I know that HPO4 is a base, so I will say that this one here, whoops, I want that as a line. This Kb is equal to 1.9 times 10 to the negative 3, right? And the Ka value is 2.4 times 10 to the negative 5. Which one is larger? Okay, this one is larger. So this one occurs more, produces more of these than these do occur, right? So if more of these occur than this, overall there's going to be more of these than these, and therefore it's going to be basic, right? So the idea is that the relative amounts of these two values determines the overall nature of this particular amphiprotic substance, okay? And so here, this is a basic substance, okay? This was explored in a WACE exam question where it asked students to explain why potassium hydrogen sulfite produces an acidic solution when dissolved in water, while potassium hydrogen carbonate produces a basic solution when dissolved in water. Okay, so we'll deal with this first point in another lesson, why we have to talk about the potassium, but when you're comparing things, you should compare the similarities and differences, and that's a similarity, right? Then we have the idea that these two substances undergo hydrolysis reactions, so they react with the water somehow, okay? Then the HSO3, the hydrogen sulfite, reaction that produces H3O+, that's the acid reaction occurs to a greater extent than the reaction that produces OH. So the acid reaction, the Ka is greater than the Kb. All right, that's the idea there, that out of the two reactions, one of them occurs more. Okay, for the other one, the hydrogen carbonate ion, right? Out of the two reactions, the reaction that produces OH occurs to a greater extent than the one that produces H3O plus, right? So that's why that one is basic. All right, we'll go through this one in another lesson as well, and then we have some equations there to show that, these are the two possible equations and that which one will occur more than the other. All right, so that's Ka, Kb, and amphiprotic substances. We'll move on to the next video. Adios.